This video is about building 3D graphics from scratch. If you think 3D programming is complicated, intimidating, and requires expensive hardware, you're not alone. Remove that hardware and 3D is just a few basic concepts, so I tried building them myself. This video is what I managed to achieve. I went from barely understanding how to represent a 3D world to implementing a reasonably accurate 3D engine. It's not Unity or OpenGL, and it contains a few bugs, but I have a much greater appreciation for the effort required. Let's look at possibly the most challenging task a computer can do: draw 3D images. Imagine for a moment it's the 1970s. Computers are pretty slow and have very low resolution screens if they can draw graphics at all. If you work in a university and have access to powerful computers, you might be able to make a few dozen frames that look like this. Or spend months doing PhD level research to create things like this, which use nice shaded polygons to give a decent representation of 3D shapes and a hint at surface texture and lighting. Skip forward 10 years, and for the majority of people, we still had slow computers that could barely do graphics at all, and if they could, the 3D looked like this. Just basic wireframe shapes floating in a sea of black, with maybe the objects rotating and scaling on the screen. This is Elite. Developed by David Braben and Ian Bell, it uses a lot of clever tricks to pull off this on a low-powered 1980s computer. And it does those tricks incredibly well. For an age where home computer graphics were sprite-based, seeing fluid 3D motion at home was really impressive, even if we really didn't understand how to play the actual game. This is going to be the benchmark for our efforts today. If a BBC Micro can do 3D, I can figure it out on my modern PC, without involving the GPU. Why am I showing you old games and sounding like a history channel? What if I told you the underlying techniques haven't changed that much? Those primitive 3D shapes were drawn in the same way a modern PC draws its graphics. I wanted to implement my own basic 3D rendering system to experience what it was like doing all of this by hand as if it was the late 80s or mid 90s. A time before dedicated 3D hardware was common, so programmers had to do everything manually. But first, we need to talk about the concept of 3D and what it even is. Right, welcome everyone to a basic perspective drawing lesson. Today we're going to learn how to draw some 3D images using one-point perspective. What you're going to need is, the first thing is to get your piece of whatever it is, I can just draw a straight line across it. This is going to be your horizon. Then what you need to do is draw some diagonal from a center point. That's going to be, start joining them up with straight lines. So you can see the thing that we're building, and you can see how the construction lines help. The drawings, are based on basic rules that we intuitively just understand by existing in a 3D world. Items at the front are bigger than items further back.
These are small, but the ones out there are far away.
There's just enough information for our brains to understand this is supposed to be 3D. So, your homework for next lesson is to draw a complete street with buildings on it using this technique. So how do we turn a bunch of lines on paper into a computer simulation? Well, the secret is maths. Is this maths complicated? It is, yes. Yes, it's very complicated. But only if you're trying to derive it all by hand from scratch or force it to fit inside an 8-bit CPU. Otherwise, it's a bit more doable. But I have a problem. My maths is shockingly bad. I've played about with 3D before, but never really understood what was actually going on. So when I found problems, a bit like today with AI, I had no idea how to go about fixing it. The maths looks like this. And that makes no sense to my brain at all. Just can't understand that stuff. So I bombed out of physics at college. It's just full of all that maths nonsense. I understood the concepts, but could never do the actual calculations. But I don't need to know the maths, I just need to know how to use it. And because it's not the 1980s, this is a solved problem. We know how to draw 3D now. I found this very helpful video that explains the process. More importantly, he's got code and he takes you through it. All right, it's JavaScript, but nothing's perfect. It's still code and I can understand it. So if you're a bit mathematically challenged, Maybe you aren't. Maybe you just need to find the right way to fit it in your brain and understand it. But I do like this idea that he points out.
You have to just shut up and calculate.
And we're programmers. We'll be doing that quite a lot. So let's start at the beginning with some Wireframe 3D. By doing this, we can investigate the techniques for drawing 3D looking images on a 2D screen. I'll start with a simple cube and then we'll go from there and see how far we get. The general idea is that we define objects using points. These points are defined as X, Y, and Z coordinates. Putting this on the screen requires converting or projecting the 3D points into 2D positions. The basic version merely requires dividing the X and Y components by the Z component. I believe this gives an isometric view rather than a real perspective view, but it's good enough for what we're doing. But something's not quite right here. This doesn't look very cube-like, really. However, with some basic maths, the points can be rotated, showing all 8, and then connected with lines to create a wireframe model of a cube. And if we use that rotation math some more, the cube will appear to spin. So following the video from earlier, I was able to get this working in Python fairly quickly. Python isn't really that good for this, because you've got to jump through a lot of hoops, because it just really doesn't do structures. You have to pack things into arrays, or put them inside dictionaries, and it generally just gets really messy with lots of square brackets and speech marks and things. It's not a very clean system. But either way, the code sort of works. But the end result is still really quite pleasing. It doesn't look like much, but getting here was so satisfying. It showed me that maybe 3D wasn't as complex as I assumed. Or is it? What if I told you a cube is boring? A cube wouldn't have done it in 1970. Let's do something a bit more interesting and a bit more on topic. This is a teapot. It's a bit famous in computer graphics, hand measured and drawn on paper by someone called Martin Newell in 1975. It's pretty much the hello world of 3D graphics, the first thing you put on the screen. It's an object that's sufficiently complicated enough to show your rendering is working properly. It also lets you put surfaces and patterns and get lighting working. It's a bit better than a cube. Now, Martin Newell was a bit of a big deal in early 3D graphics. Now just imagine this for a moment. Today, if you wanted a 3D model of a teapot or a hand, you'd either just get one off the internet, or sit down in Blender, or whatever you like, and construct it from shapes using a computer. Well, when this original teapot was created, those tools didn't actually exist. There was no software. So he literally sat down at a table and measured a teapot to figure out angles and numbers that describe its shape. And then he wrote them down on a piece of paper and got that into a computer. You know, I'm doing coding the sort of difficult way. They were doing it actually the hard way because they were inventing everything that now exists. You've got to start somewhere, and that's how you begin. Fortunately for me, someone has turned this into a data file that is very easy to load into software. What you're looking at is known as a wavefront OBJ, I guess. We're not supposed to speak file name, really, are we? It's a very old text-based format for storing a list of points, and then how those points are linked together. The points are called vertices. Linking them together forms faces. And it doesn't take much effort to alter the code above, so it loads and draws a wavefront file. I mean, okay, you've got to actually parse it through, but because it's just text-based fiddling about, it's not that difficult to really do. So I've got the teapot spinning around on the screen, and it's nice and everything. But there's one major problem that you can probably see, and seeing is literally the problem. We can see right through it. Not even Elite on a 1 MHz BBC Micro had transparent objects. So we've got to level up our graphics drawing abilities and figure out how to hide parts of the objects so that they feel more solid. If we just examine the object file for a minute and look at the list of faces, they're shown in groups of 3. And actually, I'm quite surprised my previous code even draws a teapot at all and not just this weird mess. It's literally missing 1 point from every face. I guess the faces are numerous enough that there's no holes. It's a bit of a bug and I didn't really notice. But knowing 3 points describes every face makes the next part of our strategy quite simple. Because let's stop drawing lines and draw triangles instead. Because triangles are the basic shapes in 3D. Everything is turned into triangles. Your extremely expensive video card exists to do two things very, very quickly. The first one is multiply banks of numbers. The second one is draw triangles. And maybe you don't actually have a graphics card because someone else bought it and they're using it to mine Bitcoin or calculate AI responses. But that's just multiplying numbers. I just needed to slightly edit the code that loads in the points to include the third point that I should have done in the first place. And then add a little bit of code later on to draw triangles instead of lines. And there we go. It's, it's solid, but can you spot a problem? I can. There's now no form or shape at all. It's just the silhouette because there's no lighting, there's no shading, there's nothing to tell our eyes there's any depth. But that's not actually the real problem. If I slightly modify the code again to give every triangle its own colour, the real problem becomes a bit more clear. The teapot is weirdly like it's transparent, but it also isn't. And I don't mean it looks like glass, I mean it's weirdly competing with itself. Our brains are having a hard time working out what the object should look like, which bit is inside, which bit is outside. We've not evolved to see both the in and outside of an object at the same time, so our brains can't do this. Even Escher would have had a hard time making sense of what we're looking at. Here's where 3D graphics get tricky. Drawing shapes on a 2D screen is easy. Making them look solid, not so easy. You see, the thing is, the renderer has to figure out which triangles are visible and only draw those triangles, so that objects that are in front hide the ones that are behind. You can't have like the front ones and the back ones in the wrong order. And it involves two steps. You've first got to work out which triangles face away from the viewer. They're the ones that you shouldn't be able to see. Then you have to sort the triangles so that when they're drawn, the near ones cover up the far away ones. It's a bit weird because in real life, everything's got a front and a back. Okay, that's the front of my hand, that's the back of my hand. They look objects. In graphics, triangles don't have any width. So you just have to decide that you're only going to look at one side of them and that's called the front. The other side doesn't exist. It's called a back face. And it's what you'd see if you could somehow get inside a solid object. It's physically impossible, but this is part of the weirdness of simulating reality on a computer. We have to deal with these odd edge cases. What we're doing is known as back face culling, and even Elite on the BBC Micro used this, which is surprising really. I'll show code and maths on a modern PC, but this was being done nearly 50 years ago. The maths is quite tricky, but that's kind of the point. I want to write the code to grasp the concepts behind the maths, not necessarily the exact maths itself, but why it's needed. You see, I'm not a mathematician, I'm a programmer, so any maths that I ever saw in code was just this weird, unknowable stuff. But by doing this little activity, I'm starting to understand that maybe it's not as complicated as it looks. So we've got this concept of something called a normal. This is a line that points away from every triangle at 90 degrees. We can use that to work out which triangles are facing the viewpoint. It uses two maths operations known as a dot product and a cross product. They're just fancy multiplications, because 3D maths, like I said before, mostly involves multiplying numbers. And multiplication's not that difficult, anyone can do it. So here's a spinning cube with the back faces removed, and this is also really pleasing. I made this myself, it's cool, I like it. And if I try it with my teapot code from earlier, it's kind of working, but we can see that because the teapot is known as what's a closed mesh, it's like a complete container. You could 3D print this. You can see it's inside showing through, and it appears to be upside down, and only shows every other triangle. I've got a few bugs. We'll fix all that mess in a bit. Stuff never works like you think it should, you know? Let's find out why this is not working properly. A simple method to ensure objects are drawn in the correct order is called the painter's algorithm, which mimics how painters layer images. First you start with a background, then you draw some happy little clouds over the top. Then you get your big mountain and you paint it on the top of that, and then you layer it up and so on. Martin Newell measured his teapot to explore ways of drawing 3D scenes, including the idea of using the painter's algorithm. He didn't invent it because it's a sort of like fundamental obvious idea of drawing stuff, you know, things go on top of each other when you paint. But he was testing if it could solve problems like what we have with trying to get the right triangles in the right order. It mostly works. There's a few strange cases where If you have intersecting triangles, it doesn't know which one to draw first. But it's good enough for my needs. So let's try it with the teapot before. Well, no, that's clearly not working, but it is the right way up this time. I've got my suspicions about what's going on with this, and it might not be entirely my fault. Although this is the kind of issue that happens when test code that you've knocked together is given more complex data to work with, it will always break in weird, strange ways. However, if I just make the code order the triangles by their depth and don't attempt to choose the triangles based on their direction, it works fine. But it is a bit slow, because it's drawing all the triangles, including the ones you can't actually see that it doesn't need to draw. Because there's no way drawing one single object should use 6% of my CPU and peg one core of my machine at 100%. This isn't a 1980s PC. This is a pretty modern computer. It should do this in its sleep. Now, since I got this object off the internet using a random Google search, it's possible there's problems with the model. Drawing 3D models correctly relies on the triangles making them up being defined in the correct order. This is known as their winding order. What order do you go from point to point when drawing a triangle? Do you go clockwise? Do you go anti-clockwise? Well, it doesn't really matter. You just have to be consistent. You can't have half your triangles going one way, half going the other, because the order defines which way the normal points. To work out the normal, we have to do certain maths using the points. So it matters which way around we do this. And I think the problems that I'm seeing are that some of the triangles have a reversed winding order for some reason. Although really, since because I'm writing this myself in crappy Python, it's more likely 100% my code's fault. Or maybe not, because I found another version of the sacred teapot. And while poking through its data, I noticed there were surface normals that were already computed. I mean, if you were making a 3D tool and designing objects in it, you'd make that 3D tool pre-compute the normals and export them in the data file as well, wouldn't you? Because yes, even Elite did that back in the day. And after a little bit of trial and error, and then a lot more error and a bit more trial, but mostly errors, I've now got a nice spinning teapot that looks like an actual object. This was another moment where I felt like I understood a concept I'd previously discounted as far too difficult for me to understand. The code works in several parts. It correctly orientates the normals to match the triangles they belong to. If you rotate a face on the model, you've also got to make the normals point the correct direction as well. They're not magically just there. Then there's some slightly mad maths to work out the center of the face to stick an average of the vertex normals to, because you get like, for each point you get a normal, but I need one for the face. So I've got to add up all the points that make up the face to work out an average, which is then used to work out the normal vector towards the camera. And we use dot product with the normal to work out that vector. If the normal is pointing the wrong way, we just throw that entire triangle away and don't even bother trying to draw it. Otherwise, we compute the average Z value of the face, stick it in a Python list and sort the list by depth. The camera is always looking down the Z axis, so items further away from us have a more negative Z value. So that tells us what order to draw things in. I've then got a separate loop that draws those triangles, which are now in depth order. This was just a little bit complicated to get working and figure out. There's lots of information out there telling you how to do like that process, but they explain it like I've just done. It's easy to describe, but turning the description into working code and then jumping through that crap Python-inflicted hoops nonsense adds a little bit of spice. So let's stop doing this in easy mode and do something more interesting. The next part is going to take some work. So far, all we've done is looked at a single object that's right in front of us. It's now time to pick up the camera and take it for a ride, but doing that is going to require a bit more exciting linear algebra. This is why we listen to maths teachers at school, kids. You get to use it to make cool graphics. Let's get to the good stuff, the part of 3D that literally everyone was avoiding until computers became fast enough. The ability to have a freely moving camera. Games became much more immersive when the viewpoint could be controlled by the player. They were no longer watching events happen, they were part of them. They were the camera director as well as an actor in the game. So all the hands and the teapots and the 3D games that we've ever played up to this point, including Elite in a kind of weird way, all used fixed cameras. I know in Elite you can steer the ship and look where you want, so technically it does have a camera. But I get the impression that it's a spaceship game because it neatly hides the slowness of the algorithms on such primitive computers. I get a feeling they were trying to just make a 3D game of some sort, and since we can more readily accept flying in space might look slower than a first-person shooter that chugs along at 3 frames a second. I could be wrong, but then again, here's Alone in the Dark on a PC. It looked impressive with 3D characters walking around the screen, but the camera was like you're looking through a CCTV camera. And after making this recording, I've got to say, it made the game pretty much unplayable. It's got those funny old style tank controls, where left and right is swapped backwards when they're walking towards you. And you can tell from the frame rate there was a hardware limitation that they turned into a game mechanic. But just the viewpoint and the controls just doesn't make it easy to play. You can get stuck in that point of the game where it switches between 2 different camera views just because you've moved a little bit. It wasn't until Descent appeared that we got proper 6 degrees of freedom and a camera that you could really control with the mouse. But this was the 90s and we hadn't yet invented all the conventions that we take for granted today. If you play a game now that's got a camera, you pretty much know the left thumbstick is going to move your view and the right thumbstick moves you around the room. Or if you've got a mouse, the mouse will control where you're looking and then the keyboard controls movement. At this point we hadn't yet invented that. If you notice, at this point I flipped upside down because it inverted my mouse and I could actually make it more playable because up was up and down was down like I'm used to. But then Quake came along and changed literally everything. It had a proper 3D camera with a first-person view. The kind of thing we take for granted today. Like you would not play a 3D game today if it didn't have a first-person view unless it was being stylistic and fancy. Although even then, it was an option you had to physically switch on and the game was playable without it. I remember having to learn how to use a mouse and a keyboard at the same time to play a computer game. Until then I'd just been used to using a keyboard. So the concept was so new they had to hide it by default. And I want to implement one of these myself. A proper 3D camera that you can move around the scene with. First, I need to switch tools and recreate my demo program in something better. This Python is getting very fiddly to deal with. So bear with me while I just rewrite it in C++ like you do. And instead of manually doing all the maths, I'm going to use a pre-written library, which isn't cheating. It just saves me a lot of effort. I'll get to that in a minute. The code so far has shown me firsthand why nobody writes a 3D engine by hand anymore. There's a lot of tedious coding that's needed to implement the maths. The maths itself is done, but you've got to code it. So vectors and matrices need turning into C++ classes with function overloading so that operators like adding and scaling vectors work. Then comes testing. You've got X, Ys and Zs everywhere in the code. And it means a single typo can cause subtle errors. Swap an X and a Y, it might look fine until you move something. Since I'm not a maths channel, we'll just grab a pre-made 3D maths library and use that. I am still rendering all of this by hand though, by drawing triangles. I'm not just switching to a 3D API. And this is where my maths needs to change too. Currently, I'm using a lot of procedural maths, written like a programmer. There's functions that do one specific task like rotate around the y-axis or translate down the z-axis. And I'm just chaining them together one after the other as I think about what it needs to do. Programming is actually an extreme version of applied maths. So all of this can go away and just be represented by just maths. What I need to use are things called matrices. They're a more compact way to represent translation, or scaling, or rotation, and 3D projection. And really all they are is 2D arrays of numbers. When I did my university course and we learnt about matrices, I looked at them and went, oh, it's a 2D array. I kind of understand this. This isn't too intimidating. And if we do specific multiplications to these numbers, it allows 3D points to be transformed, rotated, scaled, or translated. And that's what a camera is, just a matrix of numbers. In fact, from here onwards, the entire 3D engine is just a stack of matrices that transform 3D points. This is also exactly what Elite was doing back in the 1980s, on a computer that had no ability to do floating point maths, with a 32K of total RAM at 1 MHz. No, it didn't run Crysis, This was the crisis of its day. It all starts with objects. While you can make them by hand, it's far easier to create them in a proper 3D modeling program. That software has its own coordinate system, and it usually makes sense to create a model with the origin in the middle of the model. This coordinate system is called object space. All the objects need putting in the world together to create a scene. This is called world space. What it does is defines how the objects are orientated towards each other and how they're positioned to make up whatever it is you're trying to look at. We're looking through a camera into the scene, but really, as far as the maths cares, the camera isn't an object that exists. The camera just describes how the 3D points in world space need translating so that the part of the scene we want is within the camera's viewpoint. And when you move the camera, really what you're doing is moving the entire world in the opposite direction. So if you're playing a 3D game or walking forwards, it's actually not you that's moving forwards, it's the entire everything around you that's moving towards you. After that, the points are turned into 2D to create the image on the screen using a projection matrix. The code to do this is remarkably straightforward. The magical part of using matrices is it doesn't matter what transformations are being done to the objects in the scene. Like, what I mean is there's no need to conditionally figure out whether object A needs rotating or object B needs scaling. They just have their own matrices that you modify and multiply it all together. It turns into what is actually a pipeline, and you can see why we can turn this into hardware. The code works surprisingly well considering I've not optimized anything. Moving the mouse makes the view move, and if I had more time, it'd be fun to add a floor so the teapot isn't just floating in a black void. It's a bit hard to judge that I am actually moving around and it's not that the teapot is moving. It does go really weird if I fly through the middle of the object. It's like the entire universe turns inside out and it's a bit weird and I don't understand why that's happening. Like, I can fly past the object and it's fine, but if I fly into it, it all goes weird and my controls reverse. I don't understand that bit. Very odd. This was a fun learning exercise, because 3D has always been this mystic collection of complex math that's seemingly impossible to figure out. 20 years ago, I was fiddling about with OpenGL on my Celeron Linux machine, following those classic neon, helium, or whatever you call it, OpenGL tutorials, looking in my OpenGL Redbook, and I could never get beyond drawing cubes. Later, I tried some OpenGL ES programming on an early iPad, and I managed to make a basic 3D engine, but I had no real clue what was actually going on. I just had the OpenGL Redbook, and I sort of copied example code off the internet, and then beat on it hard enough until something worked. And to make that work, all I was doing was shoveling 3D points through the OpenGL matrix pipeline. The hardware was drawing everything for me. But this here, I actually understand it. I think the bit where it clicked was when I hand-built all the rotation maths by hand and then replaced it with matrix calculations. And I didn't chat GPT at all. I actually sat down and taught myself how this works. I made a bunch of notes and thoroughly enjoyed the process of just sitting down and learning stuff. This is not a segue into an ad-sponsored section, so don't click off. Just not all coding has to be purposeful for making an end program that will be used. Sometimes it's just a practical way to understand something or learn things. The code isn't perfect. It's got weird bugs when things get to the edge of the viewport. If you look at the screen, like bits of the triangles vanish and I don't have a clue why. But I don't actually care anymore because I think I've learnt enough. My curiosity has actually been satisfied doing this. I'm not trying to write a real 3D engine that I'm ever going to use in a game. And that's the thing. I now really appreciate why games had very simplistic 3D environments and why Quake and Descent was such a big deal. Like, Quake was pretty much a proof of concept, first-person shooter with real 3D. But all that matrix maths is being done on an earlier Pentium PC, and it still has enough leftover CPU time to actually run a fun game. The hardware in our modern PCs and our phones and tablets is doing the exact same thing, in the exact same way. It's just using purpose-built hardware to make it faster. And I now 100% fully appreciate why nobody does this anymore. Nobody but weirdos like me are trying to write 3D engines by hand. Because it's that kind of thing that drives you insane. If I was trying to fix that bug where it doesn't draw the triangles properly, I could spend months on that. And if I was doing this for real, I'd just use actual hardware in my machine, the graphics card that's built in, and it will fix all those problems. Or I'd use a real game engine that's abstracted all of this away from me instead. My nostalgia tinted monitor made Quake in software mode at 320 by 200 look amazing. Seeing it again, is a bit low resolution, fuzzy mess, and it's difficult to actually understand what you're looking at. It's amazing how our brains just kind of filter that out. Causes me a lot of amusement knowing that while I've hand drawn the triangles, really now they're being rendered by like the hardware in my computer that is always 3D. If you've not realized, your screen is just a 2D texture that's then put onto a rectangle by whatever window manager or software you're looking at the moment. That YouTube video you're currently watching is actually just a texture mapped onto a big box. That's why when you like Alt Tab and stuff, you can see a live preview of the video still playing. It's not playing two videos, it's just all 3D. So it's like I'm doing 3D in my 3D, which is possibly the ultimate irony. You can't do 2D graphics anymore. There's no just frame buffer to draw on. You're ultimately just doing the texture on a 3D map surface. It's just triangles all the way down. And on that note, I'm going to leave you, and I'm going to play around with some code. And then I'll see you next time. If you like this stuff, I've got a Patreon. The link's up there, wherever it is. You know how those things work. If you made it this far, there's a subscribe button too. If not, I'll see you later. Got a new cat shirt. What is this on here? Like, I know that's a screaming cat, but what is it? A taco? I don't buy these. These get bought for me. They just appear, and I put them on. So, yeah. Anyway.